This is lecture 6. So in the previous lecture, we saw a very rudimentary receiver architecture, and that was essentially your antenna. There was a filter, very sharp filter, which typically sits off chip. The surface acoustic wave filter. Center frequency of the filter was tuned to be the frequency of interest, right? So this was tuned to be around omega LO, and we had a low noise amplifier, basically an amplifier which does not add too much of noise. Then we had a mixer, which is essentially a multiplier, and this fundamental frequency was set at omega LO, and then we had a low pass filter, right, with a bandwidth of omega VB, and the output comes out, and then it's a low frequency output. Then you can probably sample it and digitize it and do whatever you want, right? So as it turns out, even though this receiver architecture looks like it includes everything that we can think of, there are some non-idealities in some of these blocks which makes this particular receiver architecture infeasible in many applications. Okay, so in the next few minutes we are going to talk about those issues, and then see what are the alternative receiver architectures which are used in modern radio receivers. Okay, but before going there, let me also give you an electrical analogy of an antenna, right? So till now you see that the way we have been dealing with is this side is electromagnetic wave, this side is EM, and this side is INV, this is currents and voltages. So the antenna is nothing but it takes the EM wave and converts it into currents and voltages, and vice versa, right? So it takes the EM and converts into currents and voltages in a receiver. If you are thinking of a transmitter, then it takes the currents and voltages and transforms them into waves, right? Into electromagnetic waves. This is not a course where we are talking about antenna. So we need a model for an antenna which gives us an equivalent to do a circuit analysis. And as it turns out, a very simple but surprisingly not so inaccurate model of an antenna is that of we will model an antenna as basically whenever you see an antenna in this course, an oversimplified version of this is nothing but a voltage source with a resistance R, right? And you can make this resistance to be whatever resistance you want, but generally this value of R is set to 50 ohms. Okay, so this is what we will model our antenna as on the receiver side, right? So this is our antenna model at Rx, right? At Tx, the source will not be there, and it will simply be a 50 ohm impedance. Okay, so that is something we will keep in our mind. Okay, fine. So which essentially means that I can basically replace my antenna with, for all practical purposes, as a voltage source, which is VRF, and an R, and then you have a SAW filter, and then you have an LNA, then you have a mixer, then you have a low pass filter. Okay. So now the quirk that I was talking about for this particular architecture is as follows. Now, uh, now note that, so to appreciate the problem associated with this, I'll have to talk about one scenario uh, which you will have to kind of take at a face value for the time being. Now, note that each of these blocks, other than the SAW filter, will be made using transistors. Eventually, they are made using transistors, and transistors. One characteristics of the transistors is the fact that you have capacitances between each terminals of the transistors. So, as it turns out, no two ports of a transistor are perfectly isolated, right? So, if you have a signal in one port, if you have signal in one port, you are going to have some fraction of the signal in another port, even if you have multiple transistors connected to each other, right? Simply because the signal will find a way of going to the other port. Now, if we just follow that line of reasoning, then it should not be hard to appreciate the fact that if the mixer is made using transistors, there will be a path for this mixer, or rather, there will be a path for the input for the LO waveform to get coupled to the input port of the mixer, right? So LO can couple the input port of the mixer. So now, what happens if the LO couples with the input port of the mixer? So if the LO couples with the input port of the mixer, then the frequency of interest at the input of the mixer is also at omega LO, right? The frequency that is getting coupled at the input of the mixer is also at omega LO. So this coupling is at omega LO, right? It's in and around omega LO, isn't it? Now what's the problem? The problem is, note that your signal is also around omega LO. Your signal is VRF is also around omega LO plus minus delta omega, right? So this signal also comes in here omega LO plus minus delta omega, and this signal also comes into the input of the mixer. Now there is no way for the mixer to isolate the mixer's input port to isolate between the desired signal at omega LO plus delta omega and the omega LO that is getting coupled through, right? So the mixer cannot distinguish, which means between the leakage and the signal around omega LO. Now you might say that I'll ignore the signal at around omega LO. I will only take omega LO plus delta omega. But the issue is, just like anything else, we assumed so far that the sinusoid that is driving the mixer is pristine. It has absolutely no change of amplitude, and it has absolutely no change of phase from the time you turned on the signal generator to time t equal to infinity. But just like anything else in life, that's not going to happen. You are going to see certain wigglings in amplitude, you are going to see certain wigglings in the phase, and that wigglings in amplitude and phase translate to instantaneous changes of frequency, which means that this omega LO is not a pristine tone also, right? So the omega LO for the clock will never be exactly equal to omega LO. It will be omega LO and plus minus some frequency, right? If you have a very good clock, that deviation will be much smaller, right? It will be very tight. Now what is smaller, what is not, we don't know as yet. sometime later on in one of the later lectures we will try to quantify that, but for the time being we should appreciate the fact that omega LO is also not pristine, right? So your omega RF, so the omega RF that is coming in to the input of the mixer kind of gets jumbled up with the mixer's own input, and then you have a problem, right? So if this is a problem, I mean there are many other problems associated with this particular architecture, but at this point in the course I think this is one of the easier ones that we can appreciate, right? So if this is a problem, then what is the solution, right? So the solution to this is basically to recognize the fact that this entire issue is happening because the leakage through omega LO, right, is exactly the same. The leakage frequency that is going to the input port of the mixer is exactly the same as the input frequency, right? So there is no way for the mixer's input to discern which one is of interest and which one is of not. So what is the solution? The solution essentially is to say that I will not have I will ensure that these two signals are different, right? So omega LO remains at omega LO, but my frequency of interest at the RF port should not be around omega LO, should be around something else, right? The solution is, what is the solution? Don't have omega RF or the intended omega RF. You are going to have signals at the input I mean at the antenna, whether you like it or not. You should not have the intended receiver band around omega LO, right? So why is the solution? Then this will help us use some filtering, some frequency selective filtering to distinguish between omega LO and omega RF, between the leakage from at omega LO and omega, right? So fine, let's see what we can do. So the assumption now is your input omega RF is away from omega LO, right? So let's say this is at omega LO plus some frequency omega IF. But IF, I will define what IF is in a couple of minutes. So now, if you have a SAW filter here, right? So let's get rid of the SAW filter for the time being. It's always there. We'll see what needs to happen if there is a SAW filter or there isn't a SAW filter, right? So let's first okay. So I have a mixer operates at omega LO. So now what happens? So if the input is at omega LO plus omega IF, then here also you get omega LO plus omega IF, and the output you are supposed to get 2 omega LO plus IF and omega IF, right? And assuming 2 omega LO plus omega IF is at a far higher frequency, so let me neglect that. So I am going to get only omega IF, right? And then what can I do? So now note that omega IF, right? So let me also sketch the waveform. sketch the spectrum, that probably will help. So this is, let's say, your omega LO, right? And let's say your omega RF is somewhere around here. And this gap is omega IF. Okay. Okay. So now when you get omega IF, what do you get? Down converted version is no longer around DC, it is around omega IF. So what type of filter you will need at the output? You will kind of need a band pass filter, right? You are going to need a BPF around omega IF. So here at the output you get whatever you would like to get. Now how does this solve the issue of this the LO port coupling into the input port, or the LO signal coupling into the input port of the mixer? Let's see. So if there is a coupling, this is at omega LO. Omega LO mixes with omega LO, creates 2 omega LO, which anyway we are not bothered about, creates 0 also, but now that 0 gets chucked out by the band pass filter, so nothing comes out at the output, right? So, another way of thinking about it is that now the mixer is able to discern between the leakage frequency and the input frequency. Okay, but now there is an issue with this particular architecture. The issue is as follows. Now note that we have nicely chosen the input to be around omega LO plus omega IF. If we had instead chosen the input to be around omega LO, maybe some different color, around omega LO minus omega IF, what would have been the case if the input were around omega LO minus omega IF, right? So the output would have been again at negative omega IF, but it's a real signal, so every negative omega IF will also have a positive omega IF. So you are going to have something around the positive omega IF, which means that you are going to get something at the output of the band pass filter also, but now the input was from omega LO minus IF, right? Your input was from omega LO minus omega IF, which means at the output of the mixer and the output of the band pass filter, you will not be able to distinguish the output whether it has come from the RF channel of around omega LO plus omega IF or RF channel at omega LO or RF band at omega LO plus omega IF, or the RF band at omega LO minus omega IF, right? Now I should say band, not channel, because normally these separations between omega LO and omega IF are large enough to cover multiple channels and cover bands. So this the right terminology should be omega IF is large enough to cover a band, right? So, okay, so then you might say that easy peasy. What is the solution? The solution is to ensure that this guy does not even come in. So the solution is this. So now what? Let me write down this part also. So the issue is inputs around omega LO minus omega IF can also appear at the output of the mixer and PPF. And there is a particular terminology for this. This tone, the band at omega LO minus omega IF is called the image band. It's the image of the intended frequency, right? Now note that it's not like always the omega LO minus omega IF is the image band. If your intended signal is at omega LO minus omega IF, then omega LO plus omega IF will be the image band. But there is this image band is a problem if you choose your omega LO to be away from omega RF. So what is the solution? The solution is filter the image upfront. So how do you filter image upfront? You put a filter. You are anyway putting a SAW filter, right? So the SAW filter is now around omega LO plus omega IF, right? So this also serves the purpose of, to some extent serves the purpose, or to a large extent serves the purpose of filtering out your interference from your image frequency. Okay. Now at times the interferer that comes in, your SAW filter will never be able to fully reject anything, right? It is going to only suppress. Now depending upon the specs of the band, right? If the SAW filter, let's say, is able to reject up to 40 dB, and you want another 40 dB rejection or another 20 dB rejection, then you might have to put a separate filter on chip, right? And that is often called an image reject filter, and that is surprisingly quite common, right? So often you will have to put a separate image reject filter at omega LO plus omega IF, that is the center frequency of omega LO plus omega IF, and this image reject filter sits on the chip. This is on chip, right? Now the location of the filter can be before the LNA or the after the LNA. That is a system level call, but nevertheless it is very common to see another separate image reject filter if the rejection provided by the SAW filter upfront is not large enough. Okay. So now time for a couple of jargons. So this particular topology, right, where the center frequency or the LO frequency is different from the RF frequency, it has a name. It's called a heterodyne receiver. This is called a heterodyne receiver. And the other one, where the center frequency is the same as or the LO frequency is the same as the input frequency, it's called a homodyne receiver. Now there are a couple of other terminologies also. People call these receivers in multiple ways. So this receiver is often also called a zero IF receiver. Is also called a zero. Why zero IF? Now note that it's a homodyne receiver is a special case of when I set omega IF to be equal to 0. Right? Architectural wise, that's what that is happening, right? So now it's also time for me to define or name what IF is. So IF stands for intermediate frequency. right? So obviously you see that you are not directly taking the input, right? So if the input was around omega omega LO plus omega IF, right? At the output of the band pass filter, you are not getting things around DC, right? You are getting things around another center frequency omega IF, right? So that's why it is called an intermediate frequency, because job is not yet done, because you are expecting the final band pass filter to output to be around DC, right? Because your voice signal that you are transmitting was somewhere around DC to few kilohertz, right? Or the video signal that we are transmitting were very low frequency to few megahertz. Now your omega IF can be as high as tens of megahertz to even hundreds of megahertz. So having a signal only around a band pass signal around omega IF is not sufficient, right? So that's why it is called an intermediate frequency, because job is not yet done. We are somewhere in the middle. So now what is the job? The next job will be to ensure that this I down convert this omega IF to DC, right? So what can I do? So I have now this omega IF. So the input is coming out at omega IF, and I want to down convert this to DC, right? So the next step is essentially I have to put something here so that the output is around DC. So what should I put? How do I convert omega IF to DC? The only way we know so far to translate frequency is to multiply it with another frequency. So I will put a mixer. What will be the center frequency of the mixer? So this is, I call this omega LO2, which will be centered around omega IF, and then we are going to have a low pass filter, right, with the bandwidth of the signal, and voila, the output is around DC, right? So your heterodyne receivers are typically called super heterodyne receivers. That's why I have two sets of down conversion, right? One to convert it to omega IF, and which is the intermediate frequency, and the second down conversion is from the intermediate frequency to DC. Now you might say that I have cheated, because what about the LO feed through problem, the problem of LO signal coupling into its own port for the second mixer problem, right? So if I were able to get a good mixer now, I would have used that same mixer up front. But why is it not a problem here? So indeed it's a problem. You are going to have some feed through issue at omega IF. But the question is whether this feed through is acceptable with respect to the previous one or not. In order to appreciate that, we'll have to check the spectrum of this feed through, and the answer lies in the spectrum. So let's look at the spectrum. Let's look at the potential spectrum. So let's assume that so is feed through a problem LO feed through or LO coupling a problem at IF. So that's the question we are trying to understand. So to appreciate that, let's take an example. So now what I will do, I will not take a sinusoidal clock, because that's never the case. It's almost always a square wave clock, right? So let's assume your VLOT has this waveform, right? So the fundamental tone of this is essentially omega LO, right? So that's the assumption. So let's say this, we call this TLO. So 1 over TLO or rather 2 pi over TLO is essentially omega LO. Okay, and let's assume this height is 1 volt for the time being. Okay, so now let's further assume that when this coupling is happening, it's not like the entire omega L, the entire LO port, the entire VLOT is getting coupled into in the mixer port, right? Generally tends to happen is that if we assume that there is a capacitor associated with capacitor responsible for this coupling, so think of it like the presence of a capacitor, and there is some resistors associated with it. So let's model this coupling as you have a capacitor and you have a resistor, right? And you have a square wave here, right? So if that is the case, what are you going to see at, right? So what we are trying to figure out, what will be the coupling from the LO port to the input of the mixer port. Okay, so what should it look like? This RC is classic high pass filter, right? And if the assumption is that I mean, we have done everything possible to minimize this coupling, but still there is coupling, which means the coupling will be maximum around which part of the waveform? The coupling will obviously not be maximum when the waveforms are not changing, when the waveforms are flat, because when the waveforms are flat, think of the capacitor is kind of open, right? When it is only when the waveforms are changing, when there is a sharp rise in the LO waveform, the capacitors act like a short circuit, and you are going to it's going to pass on that sharp peak, that sharp transition, and then again it is going to go to sleep, right? So essentially I can model sharp transition here goes to 0, sharp transition here goes to 0, and so on. Now note that it will never be a rectangular wave. The only reason I am drawing a rectangular wave is because it makes the maths easy, and it will also give us some intuition as to whether it's a problem or not. Okay, so the value of the rectangular wave is not of concern, or even the shape of the rectangular wave is not a concern. What I am trying to figure out is that if there is a difference between having the LO leakage at LO feed through at higher frequency with respect to lower frequency. Okay, fine. So let's if that out of the way. So now let's find out. Now note that this is a periodic signal, right? Because the clock is periodic, so the feed through will also be, the leakage will also be periodic. And let's assume that this leakage maxima is Vp, right, which can be 1 volt based on whatever we had assumed earlier. To what is the strength of the fundamental tone, because that is of interest, right? The strength of the fundamental tone will be the location of the fundamental tone will be at omega LO, right? And that location of the fundamental tone is important because that omega LO is compared with the incoming frequency also, right? So if omega LO is at the same frequency as the incoming frequency, then it's a problem. But now what we are essentially saying is that is it that much of a problem, which means that we are trying to figure out whether the strength of the leakages at omega LO is significant or not, right? So that's all we are trying to establish. Fine. So let's find out what is the strength of the omega LO component of this waveform, right? So what waveform are we talking about here? We are talking about a waveform which is like a narrow set of I'm going to say impulses, but a narrow leakage tone, right? So the height of the leakage tone is Vp, and let's say the leakage happens for a small amount of time delta t. This is Vp. The leakage happens for small amount of time delta t. What is the strength of what is the strength of the tone at omega LO. How do I find out? Again, the Fourier will be our savior. So basically we are trying to find out A1, that is strength of the leakage at omega LO equal to A1, which is essentially if I call this V leakage, it will be 0 to T V leak e power minus j omega LO T dt, right? So what is this? If I start from here, what do I see? I see from 0 to delta T, this is equal to Vp, right? Then e power minus j omega LO T dt. There is a 1 over T term, which I forgot, which is important. And then from this is TLO by 2, TLO by 2 to TLO by 2 plus delta T, you are going to have negative Vp times e to the power minus j omega LO T, right? Okay, so let's evaluate this. So A1 essentially 1 over TLO times Vp. Vp is common to both the terms, so I can take it out. This becomes power minus j omega LO T by omega LO. Is that correct? Yes. 0 to delta T. Then this is negative power minus j omega LO T plus j omega LO. Right? So I'll take this j omega LO out again, because that's kind of common between both terms. So Vp by and omega LO and TLO gets multiplied and we get 2 pi. So we get negative j 2 pi. Here we get, or I'll just keep the negative here. So here you get 1 minus e to the power minus j omega LO delta T minus, what we get, e to the power j negative j omega LO T LO by 2 plus delta T minus e to the power minus j omega LO T LO by 2, right? Okay. So I'll keep this as is, 1 minus e to the power minus j omega LO delta T minus, from here I can take e power minus j omega LO TLO by 2 common, right? Fine, so I can take that out. Note that omega LO TLO is 2 pi, so I basically am taking the minus j pi out, right? So here I get e to the power minus j omega LO delta T minus 1, right? E to the power minus j pi is essentially negative 1. I made a mistake here, so this should be plus because I took j omega LO out. So if I take j omega, or if I keep, so then this negative becomes positive. So this becomes plus. So e power minus j pi is essentially -1, and this one flips, so I get twice of this, right? So basically I get 2 Vp by j 2 pi 1 minus e power minus j omega LO delta t, which means A1 is, by again do the classic pi e to the power minus j omega LO delta t over 2 common, then we get e to the power minus j, or rather plus j omega LO delta t over 2 minus e to the power minus j omega LO delta t over 2. So this becomes, the one within the parenthesis becomes 2j sine omega LO delta t over 2. So I get Vp over pi times 2j, I check out j somewhere, should have been j pi. So 2j sine omega LO delta t over 2 times e power minus j omega LO delta t over 2. J goes. So the moot point is that mod of A1, right? Your mod of A1 becomes 2 Vp over pi times sine omega LO delta t over 2. But this does not give too much of an insight. But if I impose the insight that delta t is a small duration, that is, the leakage is happening for a small duration. So if omega LO delta t over 2 is much less than 1, right? That's a fair enough assumption, because the leakage should not be a dominant part of that. The feed through should not be a dominant part of the entire cycle. Then I can say that mod A1 is equal to 2 Vp over pi times omega LO delta t over 2, right? But the key notation here is, note that you cannot do anything about Vp, because if a capacitor, the feed through goes more or less Vp, you cannot do much. Delta t also you cannot do much, right? I mean, you can obviously try hard in the design and get these feed through times and all to be absolute times to be as small as possible, but assuming you have maxed out whatever you can do, you cannot do much. But the key thing to note is that the strength of the leakage is proportional to omega LO, right? So what is the key takeaway? The key takeaway is strength of the LO feed through is proportional to omega LO. So why is this the key takeaway? This is the key takeaway because what is the conclusion? LO leakage is much higher if omega LO is large. So or I should not say much higher, LO leakage is large, leakage increases if omega LO increases, right? So which essentially means that in heterodyne receiver, so now if I sketch the heterodyne receiver, and I'll not sketch the SAW filter and all. So let's say I have a SAW first mixer at omega LO1, then you have a band pass filter, then this is around omega if, then you have a second omega LO2 which is around omega if, and then you are going to have a low pass filter where omega BB is the pass band, not the center frequency. So then if we know that omega IF is much less than omega LO1, because omega LO1 can be at gigahertz and omega IF can be of the order of few hundred to tens of megahertz, right? So since omega IF is much greater than omega LO1, thus LO feed through, LO leakage is less of a problem at IF. Now note that it is still a problem. The problem hasn't gone away, but the magnitude of the problem has reduced, right? So for example, if the input signal is, let's say, of the order of a millivolt and the leakage is of the order of 10 millivolt, then you have a big problem. But if the input signal is of order of a millivolt and the leakage is of the order of microvolts or tens of microvolts, then it's less of a problem, right? So now I exaggerated the numbers, but you get the idea, right? So now note that these are not the only issues with homodyne receiver which the super heterodyne receiver solves. There are other issues also, but we'll get into those details later on. But I hope that so far in this course, this is the first time we are getting into slight amount of detail of what a radio receiver typically looks like, and I hope that you have been able to get a slight amount of understanding as to what goes behind decision making of the choice of an architecture, right? Okay.